Thanks. Like Alan, I changed my title dynamically to go with the flow, and since I noticed I was last on the thing, I thought I would try to pull it all together. And you know, as the last speaker, you always have the advantage of listening to all the fantastic talks. So thank you everybody for your previous talks. If we think about, this is more of a position talk. I'm not going to show a specific project per se, but in terms of human building interaction, if we, based on Jeff's folk theory point yesterday, the use of metaphor, if we use embodied intelligence as a metaphor for understanding intelligent buildings, you know, what would we put for the building? I would say something like embuilding intelligence. And of course, that's not a real word, but because of the power of metaphor, I'm sure you know what I mean. And so if we're going to have, in the description of the human building interaction field, you know, the story would be that if we had an embuilding intelligence, we could do things like assistive robots, physical therapy, autonomous vehicles, and of course smart buildings. But the hypothesis I think that I would position as being a key one would be that buildings need to know what a human is, and so that it can have behavior that we would prefer. And so the question would be, how do we expand the notion of embuilding intelligence to include that desired behavior? To expand that, we can look at things like, going back to the 1920s, Albert Schweitzer's another metaphor, the circles of compassion. And here's a moral expansiveness figure I like, which has, you know, family and friends in the middle, and then our groups, and then outside of our groups, animals, the environment, plants, and I like the one for Billings there, which has the bandit mask there. And of course, all of those things relate to buildings as well. Also yesterday, Jeff talked about, like, how do we treat buildings or robots, and how do they treat us if they're embodied or in buildings. And Peter Singer has a good book on this, the Expanded Circle. Again, talking about how to over time change our behavior. As it relates to buildings, I would propose sort of these circles. At the center, having empathy and understanding of that others have feelings, basically, which in computer science we could call sentiment detection, noticing that people have feelings, expanding that to sympathy, where we actually can share the feelings of those. And this Stanford has the paper on the machine theory of mind, where it actually has a model of what it thinks you're thinking, basically. And then the third one being compassion, where we want to reduce the suffering of others. And this could be part of a multi-objective or single-objective optimization, minimization of emotional discomfort. In building science course, we talk a lot about comfort or discomfort, and so that could be expanded to many things. Unfortunately, we don't have in-building intelligence, so we just have this thing that we often refer to in energy modeling as the light bulb, human as a light bulb, where it gives off some temperature and emits some things like H2O and CO2. And unfortunately, even that's a little generous. Like, if you look at our building in Toronto, here's a little tool we had called Dasher, building dashboard tool, where we show when we plugged in the building control system, 700 sensors showed up, including some CO2 sensors. And, you know, those are not even the people, right? Those are just on pillars or here and there. And here's a few CO2 values. We can do some things like do a heat map and interpolate the CO2 values, but that shows even more that it's not like people. And here, for example, of course that's static, so we can also show it over time at the NASA sustainability base. We ran Dasher there because they have a nice high density of sensors. And this is not CO2, this is temperature, but you can select some period of time, a day, for example, and then show how that changes over time. The server rooms in the middle are cooler. You can see the glazing experiment they did at the bottom in the middle as being effective. And this is really work we started, I'm afraid to say, almost 10 years ago, where we wanted to have, also relating to some previous talks, kind of a building debugger, because buildings are the #1 cause of greenhouse gases. They really just are horribly inefficient for many reasons, including the operator that just like turns everything off and doesn't trust the system and thinks they know better. And this was trying to match from software development in debugging to how would those same ideas of tracing a variable or setting a breakpoint, how would those apply to buildings? That was inspired by this picture that I saw of a net zero building in Denmark called the Green Lighthouse Building. And it was just, I thought it was really cool. It has all these things going on. People running around, stack effect, hybrid ventilation, some thermodynamics, day and night. And so we've been working for a number of years to sort of model these building systems, but also the system of systems and putting them all together. So we've developed and open sourced something called SciDevs, Symmetric Devs, which is based on an old system simulation theory from the 70s, from Bernie Ziegler. And we've started to model these systems together with Mobasser and others to include as many things as possible. And the unique part about this is a lot of these solvers exist today where you can run them and get something back and then send them to another solver, and it's sort of called co-simulation. But all of these things to really interact as a system have to interact and affect each other as time advances together. And so here you can actually do that. So for example, in this little hello world example of a building system simulation, we have a weather model where the day gets warmer over time. We have thermodynamics model that the building heats up from the outside until it gets to the center. There's the heat source, which is our occupant. And they have a comfort model. When they become uncomfortable, they can decide to do something like go somewhere else with the occupant planning, or open a window. And if they decide to go somewhere, there's the steering model there. With Mobasser, we've been working on that. And these things all can interact. There's loops around, feedback loops and so on, so they can interact as time advances together. So this is what this looks like. You have the building heating up while it's still cool in the middle, people running around, doing things, deciding where to go. If they become uncomfortably warm, they can decide to do something like open a window. The green flashes here. And those rooms cool down faster than the others because of thermodynamics, which affects the comfort model, which affects the occupant behavior. So this is kind of the sort of hello world of a ground truth based in simulation. It's a simulated ground truth, but that means that we know exactly what everybody's thinking and feeling. And this dev's approach supports hierarchical decomposition. So you can, my goal is to have sort of this model framework where you can add your own perception model, your own working memory model or cognitive model or perception model and things like that. So ideally there would be a framework where the community can add in just what they're the expert in and then leverage the expertise of the others. Schneider Electric was using our tool to also start to add occupant detection and an estimate of where they are relative to the sensor. Just show this also, this is an Autodesk building in San Francisco, Pier 9, where we also started working with instrumenting one of the pedestrian bridges there as an example of some infrastructure sensing we wanted to do. And it was kind of fun. With these seismometers and accelerometers and things like that, we could actually detect earthquakes as well and fluctuations in the power grid. But the intent was to see what people are doing on the bridge. And in addition to these sensors that we expected to be on the real bridge, we also wanted to actually have some ground truth. So we also added some video sensors so that we could relate the effect of the accelerometers and so on to the video. So for example, here's a specific event, which is a footstep. And on the right, we can zoom into the data until we finally get to like the millisecond level here. And see if that is a footstep compared to the video. Then we want to automate that, of course, as many footsteps with some computer vision to find these people. But that was still just saying whether there were people there or not. Wanted to go a little further and say, when is there somebody? So by using the computer vision, we have these little blue lines at the bottom here, which detects when somebody's there, so you don't have to watch hours of empty video. But even further, we want to know what are they doing. So are they walking in groups? Are they leaning to one side? Are they carrying something? So there's all these types of events that we want to capture and find out how can we rebuild the ground truth signal with these other sensors if we didn't have cameras. And then also in our own office environment, we want to do the same thing. So we've actually studied our own office quite a bit because that itself was an experiment, but I'll tell you about it in a second. And in this case also, we wanted to show that using this kind of technique, you can actually somewhat anonymize everything as well. So you can actually throw away the actual video and just show the skeletonization. This is based on an open library maybe you can use called OpenPose. And the nice thing about that is that you can still pretty well sort of get a feeling of what's going on. So people, having a conversation. The problem is, of course, with the static background, you don't see them sliding over with the chair. That's me in my office there. Not sure who's leaning against there talking to me. But it does sort of give this effect, and you can imagine that this will just be built into the cameras at some point. How do we know if they're doing the right thing, the thing that we hope that they would do? And to do that, we need the design intent. So just race through the story of our office. So this was based on work David Benjamin and some of my team to design a new office that we moved into. This is what we call generative design. So instead of drawing the design, we write a program to generate a design. So there's parameters. Then we have another program that evaluates how good that design is. And then we evolve this with multi-objective optimization, and then finally build one. So we have a simple geometric system. Takes kind of a backbone and divides it into what we call neighborhoods. This was sort of an urban metaphor for our office. And then we have these goals. And this is the design intent. So we have 6 goals in this case. Used to be outside, we want to preserve sort of worker productivity in terms of supporting the work style that they prefer and the level of distraction they would like, active space or quiet space, their adjacency preferences, and then the only standard simulation is the daylighting one. Each one of them, I'll just go through these, has its own little program, but this encodes the design intent so we can, when we observe some people doing something, we can see if it met the goals. So again, we have the generator where we generate lots of designs, and then we have the evaluator, the little radar chart saying how good did it score in all these metrics. We generate a whole bunch of them. We gather design intuition as the human design team gets some design intuition of what the trade-offs are. We select one, we built it, and I welcome you all when you come to Toronto to come through the office. As I said, we also connect to the building control system for quantitative data, and we also have an app for qualitative data. And this is the loop that we want to have to support continuous improvement. So if we're going to have something like sustainability or better buildings in the future, we need an intelligent building, but we also need it to get better over time. And this is the loop that I'm hoping we can work towards of continuous improvement. So I showed you too many things. Sorry about that. That's a kind of this is the problem with all systems people, I guess. Azam also had this kind of problem that there's many things going on. So there's simulated ground truths, estimate of human activity, some encoding of the design intent so we can see if it's working the way we hoped, and then an overall system to support continuous improvement. And hopefully that can be supported with in building the intelligence. Thank you.